We will need to learn some operations of matrices to proceed with our study of linear systems of differential equations with constant coefficients. We will write a generic n by n matrix as A equals A11, A12, across the row to A1n, and down the column A11, A21, down to AN1, all the way through our matrix, all the way down to ANN. We will call each value in the matrix an entry. We will call each horizontal set of entries a row, and we will call each vertical set of entries a column. The indices of an entry, Aij, give the row and column of the entry. For example, the entry A21 is the entry in the second row and the first column. We will sometimes write the entry in the ith row and jth column of a matrix A as Aij. In general, the number of rows and columns of a matrix can be different sizes. However, in our study of linear systems of differential equations, we will restrict our study to square matrices where the number of rows equals the number of columns, which we will usually write as n. The first operation that we will look at with matrices is addition. When we are adding two matrices A and B, they must be the same size. That is, A and B must have the same number of rows and columns. If we meet this condition, then to add two matrices, we add entries that are in the same location. That is, if we add two matrices A plus B, then the resulting matrix we can find entry by entry. In the first entry, that is the first row and first column of our new matrix, we'll add the entry in the first row and first column of A to the entry of the first row and first column of B. A11 plus B11. Going down the column, our next entry will be A21 plus B21. Notice that the entry in the ith row and jth column of our new matrix A plus B, which we write as A plus Bij, is given by Aij plus Bij. Computing this for every entry in the matrix, we find our matrix A plus B. Let's look at an example. Let's add the two matrices 1, 2, 3, 4 plus 3, 8, 6, negative 2. Adding entry by entry, we'll get our first entry of A plus B as 1 plus 3, which is 4. Then we'll have 2 plus 8, which is 10, in our next entry. 3 plus 6 gives us 9, and 4 plus negative 2 gives us 2. So 1, 2, 3, 4 plus the matrix 3, 8, 6, negative 2 gives the matrix 4, 10, 9, 2. Now we'll talk about multiplication with matrices. Multiplication with matrices depends on what we multiply the matrix with. We can multiply a matrix with a scalar, a vector, or another matrix. We will start with multiplication of a matrix with a scalar. For a constant scalar C and the matrix A, we define multiplication C times A, which we can rewrite as C times the matrix A11, A12, and so forth, is given by C times A11, C times A12, and so on through the matrix. That is, we multiply each entry of A by that scalar C. For a matrix A and a vector V, A times V is going to give another vector. So we need to know how to find each entry in the vector. The entry in the ith row of the new vector will be found by taking the dot product of the ith row of A with V. For example, to find the first entry in V, we will take the dot product of the first row A11, A12 down to A1n with our vector V, V1, V2 down to Vn. This gives A11 times V1 plus A12 times V2 plus all the way down to A1n times V. Computing this for each of the n rows of A will give us our new vector A times V. Let's look at an example of this. if we multiply the matrix 1, 2, 3, 4 times the vector 3, 6, we'll get the first entry of the resulting vector as 1, 2 dotted with 3, 6, which is 1 times 3 plus 2 times 6. And we'll get the second entry of our new vector by taking the dot product between 3, 4 and 3, 6, which gives 3 times 3 plus 4 times 6. Doing out the arithmetic, in the first entry, we'll have 1 times 3 is 3, and 2 times 6 is 12, so we'll have 3 plus 12. And in the second entry, we'll have 3 times 3 plus 4 times 6, which is 9 plus 24, yielding the vector 15, 33. Note here that in order for the dot product of each row of A with V to be well defined, we need the number of columns of A, which is the length of the row, equal to the number of rows in V, the height of that column vector V. Finally, let's look at multiplication of a matrix with another matrix. For a matrix A and another matrix B, we will write the multiplication of the two matrices as A dot B. When we do this multiplication of A times B, the result will be another matrix. So we will need to know how to find the value of each entry in the matrix. The entry in the ith row and jth column of our new matrix A times B will be found by taking the dot product of the ith row of A with the jth column of B. That is, the ij entry of A times B is given by ai1 times b1j plus ai2 times b2j down the line to ain plus bnj. For example, the first entry of our matrix is given by the dot product of the first row of A with the first column of B. We will then need to take a similar dot product to find every entry in the matrix. This may be best illuminated by looking at an example. Let's compute the matrix 1, 2, 3, 4 times the matrix 3, 8, 6, negative 2. To find the first entry of our new matrix, we'll take the dot product of the first row of A with the first column of B, which is 1, 2, dotted with 3, 6, giving 1 times 3 plus 2 times 6, which simplifies to 3 plus 12, or 15. To find the next entry, we'll do 1, 2, dotted with 8, negative 2, which gives 1 times 8 plus 2 times negative 2, which simplifies to 8 minus 4, which is 4. Moving on to the second row of A times B, we'll do the second row of A dotted with the first column of B, giving 3, 4, dotted with 3, 6, which is 3 times 3 plus 4 times 6, which is 9 plus 24, or 33. And finally, we'll dot the second row of A with the second column of B to get 3, 4 dotted with 8, negative 2, giving 3 times 8 plus 4 times negative 2, which is 24 minus 8, or 16. So we found that the matrix multiplication of 1, 2, 3, 4 with 3, 8, 6, negative 2 gives the matrix 15, 4, 33, 16. As we did with multiplication of a matrix on a vector, we also want to think about when matrix multiplication between two matrices is well defined. Here, for this to be well defined, we need the number of columns of A to be equal to the number of rows of B, so that each dot product makes sense. Now that we've defined matrix multiplication between two matrices, I would like to make a few notes. The first one is that unlike with numbers, the order in which we multiply matrices matters. That is, for two numbers A and B, we have that A times B is equal to B times A. However, in general for two matrices A and B, we have that A times B is not equal to B times A, though there are some exceptions to this. Next, I want to note that there is a number 1 that can be multiplied by any number and the number doesn't change. That is, 1 times x is equal to x, which is the same as x times 1. for any number x. Similar to this, there is an n by n matrix I that can be multiplied by any n by n matrix, and the matrix doesn't change. In other words, if we have I times m, or m times I, it is equal to m for any matrix m. This matrix I is called the identity matrix, and it is the matrix with 1s on the diagonal and 0s in all other entries. Finally, I would like to note that multiplication by a scalar c is equivalent to multiplying by c times I. That is, for a vector v, if we compute the scalar multiplication c times v, it is equal to c times the identity matrix I times the vector v. And for a matrix A, c times A is equal to c times I times A. This will come in handy a little down the road.